Welcome to Unit 6, Part 1 on Newton's first law. In the previous 5 units, we've been very focused on motion and how things move without worrying about what the cause of that motion was. That changes. In Unit 6, we're going to start our investigation of forces. And as I said, we're going to begin with Newton's first law. And to start this discussion, working up to Newton's first law, we're going to take a little lesson in history. So we're going to start back in ancient Greece with Aristotle. Aristotle had this idea that there was natural motion and there was violent motion. And if something was undergoing its natural motion, it moved to its natural place. Like earth is downward, clay is made of earth. Therefore, when you drop clay, it moves down to its natural place. On the other hand, a violent motion would be the opposite. If I grab the clay and pick it up, I have moved it from its natural place, which was on the earth, up into the air, which is the natural place for a different element. He had 5 elements: earth, air, fire. I don't remember them all. It doesn't much matter. These sorts of ideas persisted. And along with these ideas came the thought that the entire universe revolved around the earth. And that persisted until Copernicus came along. Copernicus, sometime in the 1500s, proposed the idea that the earth rotated around the sun, so the heliocentric model. And this began a new era in thinking about motion and what happens. And so Galileo grabbed this idea of Copernicus's and then went with it. And one of the things that he proposed was that objects will continue moving in a straight line forever as long as there's no interaction with the object. For Galileo's efforts, the church put him under house arrest, and that was how Galileo lived the rest of his life, under house arrest. Galileo passed away in 1642, so not that long after Copernicus's efforts. The very same year that Galileo died, another gentleman was born, and that was Sir Isaac Newton. But before we get all the way into him, let's think about Galileo's statement. Objects will continue moving in a straight line forever as long as there's no interaction with them. Does that work with what you think about in everyday life? If I take, say, a nice piece of floor and a block, and I give it a shove and send it flying across the floor, is it going to continue moving forever? No, it isn't. And why not? Well, hopefully you get the idea that there is friction here. And there are steps that we can take to reduce the amount of friction that acts on something. So if you think about an air hockey table, when the air is off and you hit the puck, it doesn't go very far at all. But when the air is on, it rides on that nice cushion, and it'll go bouncing back and forth across the table several times before it comes to more or less a stop. Right? I've always wondered what would happen if I could take and make a really, really, really long air hockey table and see how far that puck would really go. Okay, so in good scientific fashion, Newton came along and looked at Galileo's idea and then wrote his law of inertia, which is now more commonly known as Newton's first law. It's really just a restatement of what Galileo said. In good physics language, an object in motion will stay in motion with a constant, possibly zero velocity, unless acted on by a net external force. Okay, that's good physics language. There is an everyday version of this law. And you probably know it. It's the object at rest will stay at rest, object in motion will stay in motion. It doesn't have all these qualifiers about external forces and things like that. Object at rest will stay at rest, object in motion will stay in motion. In order to really understand the law, though, we need to understand what is meant by a net external force. Before we get there, an aside for units. So the units of force are the Newton, in honor of Sir Isaac Newton. And by definition, 1 Newton is 1 kilogram meter per second squared. Okay, so 1 Newton is by definition 1 kilogram times a meter divided by second squared. Okay, on to a net external force. Okay, so what is a force? It's a push or a pull. It's not a complicated definition. I've yet to see one that works better than that. What is an external force? It's a force that comes from outside the object or objects. So if you think about a train, right, I can view the train as a collection of train cars. And each little train part, so let's assume this part right here, we'll make X mark the spot. It would have, among other things, a pull on it from the car in front of it and a pull on it from the car behind it. Those forces would be external to the train car marked X because they come from things that are not included in that. If, however, I look at my train as one unit, then all these forces that connect the cars are now internal to that one train unit. And it's subtle, but sometimes you have to shift how you look at something in order to find the information you want. And we'll go into that more as we proceed through the units we have on forces. Okay, so we've got force, a push or a pull. External force is one that comes from outside the object. A net external force is the sum of all the external forces on an object. But force is a vector. It matters which way that force acts on the object in order to get a particular motion. So when we say sum here, what we really mean is we mean a vector sum. You have to take direction into account, which means when you add things up, you might have to add a negative sign. Okay, so let's do a couple of really, really basic examples. Okay, so here we have object A. It's got a 5 Newton force to the right and a 3 Newton force to the left. If I add these together, because they're in opposite directions, I get 5 newtons minus 3 newtons, which equals 2 newtons. And because the 5 Newton force is bigger, the net force will be to the right. Contrast that with block B. So now the force would be 3 newtons minus 5 newtons, which is negative 2 newtons. Or magnitude-wise is 2 newtons, but in the opposite direction. Here with this negative sign, we are assuming a positive to the right coordinate system. And lastly, block C here has 2 forces on it, both of 5 newtons. So when I add those together, I get a net force of 0. So there are forces acting on it, but there's no net force acting on it. Which brings me to a question. Can I say that no force acts on a body at rest? No. More than likely, a body at rest has many forces acting on it. But that body that is rest and is going to stay at rest will have no net force acting on it. Let me think of a good example that would help illustrate this. Let's consider a block sitting on the ground that has 2 ropes tied to it, and on either rope we have a person that is pulling. Okay, so if I think about this block, it's got at least 4 forces on it. It's got one upward from the ground, one downward because it's got some weight to it, and then one from each of the 2 people. So 4 forces. But if this block is going to stay right where it is, it's not moving, it's not going to move, no net force is possible, even though there are at least 4 forces on it. Okay, so now let's think about this. So you want to slide a heavy cabinet across the floor at a constant speed. I'm going to block those in. Constant speed. What I really mean, though, instead of constant speed, is I mean constant velocity. Okay, so in order to slide a heavy cabinet across the floor at a constant velocity, okay, you exert a horizontal force of 600 newtons. Now I want you to think about the friction between the cabinet and the floor, and whether it's greater than, less than, or equal to 600 newtons. The answer to this lies in Newton's first law. So let's back up a couple of slides. Remember Newton's first law. An object in motion will stay in motion with a constant, possibly zero velocity. Will stay in motion with a constant velocity unless acted on by a net external force. It says specifically in this problem that you want this cabinet to move with a constant velocity. Therefore, constant velocity implies that the net force equals 0. And if the net force equals 0, that means if you are pushing on that cabinet with 600 newtons of force, then the friction has to be opposing that push with 600 newtons of force. And the 2 forces are equal in order to make no net force on the cabinet, so it moves with a constant velocity. When there's no net force on an object, that has a name. It is called equilibrium. So can an object be in equilibrium when only a single force acts on it? If it has only a single force acting on it, can you get a net force of 0? So the answer here is no, right? If you have 2 forces on it, can it be in equilibrium? Yes, if those 2 forces are equal in magnitude, opposite in direction, then you can be in equilibrium. Okay. Is an object in equilibrium stationary? Well, the answer here is maybe. Might be stationary. It might not be stationary. Okay. Remember what Newton's laws tells us. It tells us that an object will move with a constant velocity as long as there's no net force. It could be a velocity of 0 that results in no net force, but it doesn't have to be a velocity of 0. It could be a velocity of 5 million meters per second, and as long as that velocity is constant, so constant speed, constant direction, that object will be in equilibrium. Okay, this concludes the first part of Unit 6. In the second part of Unit 6, we are going to look at types of forces.